8, 6, 7, vamos, 8, 9, 10. Eso. Empieza arriba. 1, 2. Si viene, recibe este 7, 3, 4, 5, 7, 8, 9, 10. Allá, Saúl.
Canelo likes his hands clean. Shit.
Great. Hello. Hi, Christopher.
Hi.
All right. Okay. Everything okay?
Yeah.
All right. Good. So sound is okay? Clarity? Is it okay, or is it a bit blurred? Or
I think so. Maybe I just need more questions to do.
okay. 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 All right. Let me see this. Okay. This is. Just a sec, because I'm. All right. Okay, so we said we will start today with the the atomic structure and particle physics. That's okay.
But at school I already finished it.
Oh, the whole chapter, all the sub chapters.
Yeah, but for the I kind of forgot the content for like the two types of hadrons.
Okay, because I had all right. Is it okay? So you are clear about the content, Chris?
Mostly.
Mostly, okay. Maybe we do a brief review, huh?
Yeah.
And I have a couple of questions, so we can then do the questions, mostly less the theory. Then do a bit more on the quarks, the hadrons, and so on, the leptons, a bit that stuff. Huh? That's usually a bit confusing. Okay, but nevertheless, then you can do. So what I just show here, I know it's from the beginning, but still, that well diagram kind of picture graph. What does it tell you? What does it show? What's going on here?
It shows that the alpha particles, if the alpha particle is not, most of the alpha particles don't hit the nucleus, so it goes straight. A lot of them will get close to it, so it gets deflected, like at an angle, and then some get reflected.
Okay, yep. And when you think backwards, so to speak, as a scientist, for example, so you're shooting alpha particles from the left side because you set up the experiment, right? And you have some ideas, some suspicions about the atomic structure, but you don't really know. Let's go back 100 years plus, right? Obviously, that's what I'm aiming at. And so you're shooting these alpha particles. Just a sec, my pencil is a bit flunking up. Okay, here we go. So you're shooting these particles, alpha particles. And by the way, what are alpha particles?
The helium nuclei.
And Yes and no. um, what is in a nucleus?
Huh? What?
When you say helium nucleus, right? So
Yeah.
what is in the? But it must be something special because when you think of the helium nucleus, um, what's going on there? Or
Uh,
what must have happened that you can use these so-called alpha particles?
they they have two neutrons and two protons.
Okay, exactly. So what is very typical for any helium? You're on the right track. Now, what you said is something special. What is special about what you just said?
They they're positively charged.
Um, Ultimately, no atom is charged, right? In some, I mean, in total. And when you have the nucleus, so is the nucleus together with the electron charged? Also, the atom is it charged?
Huh?
So that when you have an atom like helium, is it charged or no? Is it charged or is it neutral?
Normal helium is neutral.
Neutral, exactly. Huh? So, but when you look at the picture, something happens, right?
Yeah.
And it's a bit shown in the diagram. Why are these? Some of them, those who come close, obviously the nucleus. Why are they deflected? Why don't they just crash into the um, nucleus?
Huh? Right. Because they have a positive charge.
Exactly, they must be positively charged, right? But why are they positively charged?
Uh, they don't have the two electrons.
Exactly. So we don't shoot the helium out. Okay, yeah. Okay, then we are very clear about it. Okay, that's good. So we just shoot the core of it without the electrons, huh? And
Yeah.
hence worth they miss the electrons, hence they get a 2+ charge, huh? Okay. So now you're the scientist. You don't really know about the structure. You know that these you call them alpha particles for whatever reason. And of course, at that moment, you don't really know yet because we are in a time machine 120 years ago that there are these protons, neutrons, electrons, but you know you have a certain type of particle which is charged, hmm, positively charged. That we can measure somehow. And now you shoot that on a certain metal, which has the capability. Later on, we obviously use gold, as it's explained with the experiment, so you can make it into very thin foils. And when you shoot it through, you would basically expect that it goes through, right? Because they're tiny little particles, they go through. But so what you would expect from the experiment is this one, or this outcome, right? Let's say this one. This is the expectation. You shoot it through because it's a tiny little particle. There must be a structure inside who makes that foil. But strangely, some of it gets deflected. So what does that when you don't know about the inside, right? So what does that tell you when you get something like some come out like this, some come out like that, and of course some go straight? What kind of suspicion do you have when you make that experiment?
That there are uh it's not a even distribution of maybe charge.
Okay. Because when we go nowadays, of course, it's really, so maybe it's a bit difficult for us to imagine because we know so much more these days, right? But back in the days, we would have expected it's comparatively a concentrated mass, right? So we have a suspicion. Okay, we shoot a positive particle. We shoot it at something at one point at the atom, and what would have happened is that if it would be concentrated in one point, we would have expected something like this and shoot back straight out. So shoot it in, it hits the large nucleus, and it comes straight back, like mechanics, right? Normal Newton behavior, basically. If it comes in at that angle, it goes out at that angle straight. So which is not even shown here, actually. That's a bit of pity. So what we would have expected is something like the nucleus here, then in and out. Huh? So point of origin is the point of arrival, so to speak. Huh? Boom, boom. Just comes here at this time. But it doesn't. So somehow that's very strange. Huh? That means that ultimately it's not concentrated in one point. Huh? So there must be a substructure, and that's why in the end we could conclude that there's an atomic structure behind. That's actually the bottom line of the whole thing. And we call that the so-called scattering of the alpha particles. Huh? So that resulted in the nuclear model of the atom. But before that, remember, or what was another theory before? Do you remember that? It's a very kind of funny name.
No.
Okay, it was the plum pudding model of the atom. Did you hear about that?
No.
Okay, so that okay. Now I see, because that the idea at the of course it was, how to say, there was an evolving idea that you have a core and an atom, okay, but it's made like a pudding, yeah? So that you have um, uh, but with plums in it, and these are the negative charges of the pod. And because to explain that in the end nothing's charged, you have to say, well, kind of the dough is positively charged and the plums in it are negatively charged. So together they are neutral, but it's like one big massive ball, but consisting of dough and plums, right? Or something like the big dough and in which is positive, and then you have the plums in it which are negatively charged. So together to the outside, it's neutral, but when you go in, but the idea was it's a massive thing, like a ball of dough. Only the Rutherford experiment, that's the one we just talked about. This one is the Rutherford model, right? Or experiment showed that no, it's not like that. Actually, it consists of many, as we know, parts inside. So there's no dough with electrons. So nowadays we know we have the neutrons and of course the most important ones, the protons, and then the electrons going around in those so-called shells. Huh? So that was a step one with the pudding, but the two was then to say no, there's a lot of empty space. That's the point. When we think about it, basically everything consists of mostly empty space. Huh? That's the crazy thing somehow. Do you have an idea of the distances if you would transfer that into the real world size, other than the real world, into our dimensions, the dimensions we can feel, explain, see? Then would you have an idea of the distances involved, Chris?
Uh, Well, I think that the distance should be very large because, uh, because in the universe, the big stars when they collapse, they can form very small black holes.
Yeah, that's a good point. That's a very good point, actually. The distance exactly. So even in, let's say, in the macro world, like what you said, the universe with planet and stars and everything else, or let's call it the micro world, like an atom, for example, right? Those, or in the atomic subatomic level, the distances are huge between those particles. So basically, it's mostly empty space. So that was another revelation, that when they started to think about the size of these particles, which later on were identified again, neutrons, protons, electrons, that actually that should be much smaller, but it wasn't. And that was one part of it, that they realized, oh, okay, they're actually really far away. So mostly, including us, because we are made of molecules in the end, and that means that there's atoms involved and so on, that it's a really big distance from one to the other. So basically, it's mostly empty space, huh? A bit like in the universe, so to speak. Huh? Okay, so that's something I think important to keep in mind. And the other issue is then when we look at the simple model of the atom, which we know nowadays, it was only in the 30s, also 1930s, not even 100 years ago, that they still had the puzzle, that they said, okay, we have the protons and we have the electrons. That was solved, kind of. But it didn't explain the mass. Something was still not complete, a puzzle. And the solution of the puzzle was that I later identified, that then in the 30s, less than 100 years ago, identified, there's something else which we now call neutrons, which is adding to the mass of the atom. So the revelation to realize that there are neutrons was basically the discrepancy between the theoretical weight as by the model known before 1930, protons and electrons. And the electrons are basically, you can forget about the mass of the electrons, that they knew already. But when you add up the basic structure of the atoms, we know that as well. But the mass was still not explained. And that was then the missing neutrons. Huh? So, like nowadays, we still have some puzzles to solve. Maybe in 5 years, in 10 years, in 20 years, they will be solved, and then it's crystal clear. Huh? Like when we later today discuss what you said is you would like to explain once more or go through. That was not solved long ago. The Higgs boson was found practically only 12 years ago, right? Back in 2012. Before that, it was just a theoretical concept because something was missing. It could not be explained. So the theoretical model said it must be there, but it was not found. And in 2012, it was ultimately found, the famous Higgs boson, actually. Same as the quarks and the neutrinos, they were only experimentally maybe identified 20, 30 years ago. So we're talking about really uh, recent times. Okay, so coming back to the, we call that the scaling, the scale of things. And what I just asked before, so if we would have the nucleus, whatever, doesn't a hydrogen atom, that's easy because it only has one proton, right? So if we take one hydrogen atom and say, well, this has the size of a marble, so very small. And then, of course, we know there's an electron. We call that, let's say it has a diameter of 1 centimeter, 1 centimeter. And then there's the electron. So if we would make this model and say, okay, now we are to scale, so we make the nucleus, the proton, 1 centimeter in diameter, then how far away is the electron? So what would be that distance? Would you have any idea, Chris?
Uh, maybe 10 meters.
Okay, interesting. So we would, so in perspective, the 1 centimeter nucleus, and this it would be a sand corn. I mean, we could hardly see it. 1 grain of sand. Huh? So I don't know by heart the diameter of the grain of sand, but just to, so if you go to the beach and try to get 1 grain of sand, that's already very difficult. You think of a marble of 1 centimeter, then you would have to go 800 meters away. That is the distance between the nucleus and the electron, also between the proton, because the hydrogen is the most easy one. You don't have to bother about the rest of the protons and so on. 800 meters, huh? That's really kind of wow. So that's why there's a lot of empty space actually in the atoms. Huh? So, and henceforth, of course, when we think about the nuclear density, so go into a couple of numbers. So the mass of a proton is 1.67 times 10 to the power of minus 27 kilograms. Huh? And would you know the mass of an electron, Chris? It doesn't matter for what we do here, but nevertheless, what is the mass of an electron?
I forgot.
Okay, that's fine. So it's, of course, first, there's a bit a different number here at the beginning, but it doesn't really matter. It's 9.1. That's, the key point is it's 10 to the power of minus 23. Huh? 31, sorry, 23, 31. So we have 10 to the power of 4 difference. This is a magnitude 10,000, huh? 1 to 10,000. So the electron, and this is the proton. So the proton is 10,000 times more heavy than an electron. That's why we say, well, we can truly forget about the mass of the electron. Huh? And if it's 9.1 or whatever, that doesn't really matter compared to the powers here. Huh? So that's important. That's why we always can forget about the mass of the electron in all the calculations. At least unless we go into the atomic level, of course. And see, just so, and now we want to go into the density, right? So the radius of a proton, has a well, we can't really 100% give the exact value. It's within some uncertainties due to the Heisenberg uncertainty principle. So this is about 0.8 times 10 to the power of minus 15. Huh? It has a range from 0.8 to 0.86. Actually, 86 minus 15. Huh? Because it has to do with the interaction with the electron. Okay, so now what is the volume of the proton then? What would be the formula for the volume of the proton? Sorry, the other way around. Just the basic formula for the volume from geometry.
I think is 4/3 times r cubed pi.
Yeah, very good. Exactly. Okay. Yep. So we see even on that atomic level, we can still utilize the standard geometry. And so if you apply that with the values we have, I just jump ahead. That will give us 2.14 times 10 to the power of minus 45 cubic meters. Huh? I mean, obviously, it's something tiny, unimaginably tiny. Now, when we think of density, what is density, Chris? So again, we can utilize standard physics, even on an atomic level.
Just the 1.67 times 10 to the power negative 27 kilograms over the volume.
Okay, yep. Divided by our volume, so 2.14 times 10 to the power of minus 45. So that gives us around 7.8 times 10 to the power of 17. And what kilograms per cubic meter? Huh? The reason why we do that is so the proton has a density, that's what we talk about, to make it simple, of about, well, if we round up the 7.8 to another power, then we can say roughly about 10 to the power of 18. That's the density of the proton. So we talk about the proton, not to forget. So, and what is the density of water, Chris? Oops.
1 gram per cm3.
Okay, also in kilogram, because that's the easiest way. Oops. If you take the density of water, still kilograms per cubic meter. It's an easy number because 1 cubic meter is typically, as a water, it's a good reference point. 1 cubic meter of water is 1,000 kilograms. Because 1 liter of water is a kilogram, roughly. And when you look at the sizing, the density, so if you have 1,000 of those, then you get 1,000 kilograms. So that's the density of water. And if you take the density of the proton, just 10 to the power of 18, or this is 10 to the power of 3, and this is 10 to the power of 18. Now, this is incredible. Huh? So we have a relationship of 1 to 10 to the power of 15 between water and the proton. Now, if you think water could be kind of oil, just to assume petrol, of course, petrol is a bit heavier than, or gasoline, it's a bit heavier than water, but for the sake of the discussion, has a similar density. So you have a 10 to the power of 15 higher energy content in the end in the proton, because simply due to the fact that you have 10 times 15 higher mass, more mass, right? The density is 10 to the power of 15 higher. And in the end, mass equals energy, ultimately. So that means that's why you have such huge energy in the atomic core. So that's what the scientists then realized, that is, wow, there's a huge energy storage actually in the core of an atom, starting with the hydrogen, for example, the most simple of them. You don't have to bother with all the rest. And that is why then when we think of the atomic bomb or even the hydrogen bomb, actually, they have such a huge power in such a small mass or low mass, right? And just as we talk about it here, there were very, very few hydrogen bombs, luckily, because they're extremely powerful. And the fear was always, if you ignite one over ground, it could lead to a chain reaction in the atmosphere, actually, which obviously it didn't, because we had a couple of hydrogen bombs that was still done in the 50s. They were abandoned, they were forbidden. And they did one test on a Pacific island. I was completely annihilated with a very small mass, and there was nothing left anymore afterwards. So this gives us a bit an idea, right? These atomic bombs, in a positive way, when you can harness that energy instead of as a bomb, as an energy source, is of course fantastic. So if we can harness the energy of hydrogen, not as a bomb, but as an energy source, then of course problem solved, right? Then we don't have to burn off oil anymore, hydrocarbons. We don't. It's more powerful than the photon from the sun, actually, by far. And that's why there's such a focus on, because of this relationship ultimately. Of course, we can do the fission. That's what we have in the nuclear power plants. But that's just fission, right? You just split the atom. That's nothing compared to when you make the fusion. That's what it is in the end, right? Because you have the energy and you fuse those together, and then you release the energy, actually. Okay? So far, okay, Chris?
Yeah.
Okay, so to give a bit of background, huh? Okay, then that is all clear. We spend so much time. Yeah. What is just quickly? What are these A numbers and Z numbers?
Huh? I can't hear.
Did you A? They're so-called numbers, right? We know from chemistry, of course, we have that clear in mind. But here in physics, now that we go into the atomic structure, we have the so-called Z numbers and the A numbers. Do you know what they are?
The atomic mass and the atomic number. The,
Okay, yeah, it's close. It's close. It's kind of correct. What we have when I show you this, I mean, yes, in that sense, but it has to be a bit more specific in the terminology. So when we look at the A, what does that tell you really in terms of physics? Now we are when we look at particles. So
nucleon number,
yeah, exactly. And the Z Hainsworth.
proton number.
Yeah, exactly. And so we have to. I mean, you were right with what you said. It's just a bit more specific here in the context of the atomic structure that we talk about the A and the Z numbers because they will always show up, right, in the questions accordingly. Okay. Um, then of course we have one issue with forces, right? We have forces in the nucleus, but we are not going that far yet. That's only touched at the very surface, right? With the models and so on, but we don't touch that in more detail. But do you know what? We just gave you the label. What is the name of the force in the nucleus?
The strong nuclear force.
Yeah, exactly. Huh? Exactly. Nuclear force. Huh? That's this one, holding it together. And when we go, let me see. Okay. Then what we have not covered yet, this is something very important, is the what is that? What do you see here in these three graphs or graphics? What what is that all about?
The isotopes of hydrogen.
Okay. All right. Yeah. Good one. And what does it mean then when you have isotopes?
Uh, the atoms of the same element with the same proton number but different number of uh, neutrons.
Yeah. Exactly. Right. And what does define the how can you say this is this is gold or this is silver or this is lead or this is chlorine? What
By the number of protons.
exactly? That's always very important to keep in mind. Obviously, we have that very clear because when you go into this nuclear physics stuff, then it's always one thing very clear: we keep the number of protons, otherwise we have a different material. But it can happen, huh? In nuclear physics. There it can happen that actually the core, that's exactly where fission comes into place, is really changed so that we have not the same number of protons anymore. And because of that, of course, you have a different element, right? So that is why we can say by the process of radioactive decay, as we name it typically, then you can go, so for example, away from, you won't have uranium anymore, for example. Huh? So that means you really have to go into the core, basically take a proton away in whatever way. It may disintegrate, it may be shot away or whatever. We don't care right now. And then you have a different element. Huh? That, of course, was all things which were identified roughly 100 years ago plus with all the various experiments, huh? Or reconfirmed. Some of it was a model, then it was reconfirmed in the experiments that it is really like that. So now when we look into this hydrogen, what would you expect when you go from the standard hydrogen to the next one? So from this to this to this, what would you expect you could observe, or maybe, yeah, what could you observe? What could you tell about the property from the outside?
It becomes less stable.
Less stable, okay. And what would be, let's say, you could liquefy it, for example, and I mean, as a gas doesn't matter, but let's take liquefied. It's usually a bit easier to imagine. And you take a certain volume or a container full of that. And you then have type 1, type 2, type 3. Huh? You don't know yet what's going on inside, but you can see there's some different properties. So what would be one of the most striking different properties from this to this to this?
The density.
Okay, you may say that to some degree. Would you remember why there's some name for that as well? Typically, another one, more popular name that gives a bit an idea. When you look at the structure, as I say, you would not be able to look inside, so you could not tell about the differences, right, of the structure inside, because you can only look at it from the outside. But when you look at it, like when you could measure something, what would be the difference what could you measure, Chris, and what would be then the difference?
The boiling point.
Boiling point? What else? When you think of, when you look at this one, at the top part,
The
like you
mass.
said, mass, exactly right. So you would have actually have the same element, but a very different mass. Huh? Especially, of course, on the level if you only have one proton and then you add another neutron. Does the neutron have the same mass as a proton?
Yeah.
Yeah, exactly. Huh? Important to remember. That's one of those experiments which prove that you have the same mass because, amongst others, because of this experiment with heavy water, it was sometimes then called. Huh? So it's unstable as well because with two protons, two neutrons, excuse me, that of course is not a solid state actually. Deuterium or tritium. So that's why deuterium was very much sought for in the search for creating at that time an atomic bomb. So that was very important. You had to create that so-called heavy water, the deuterium. And that was then a one base in order to continue further with the development of the atomic bomb. Okay. Have you ever seen a picture like that, Chris?
Huh?
That picture now? I can't. Can you see it, or is it gone?
Oh, yeah, yeah, yeah.
Okay. So, have you ever seen anything like that, or a similar picture? It doesn't just have to be this one from the universe. Some
Yeah.
So, when you look, how come we have these colors first of all, and why is it not just black, or just the planets? Sorry, the stars glowing. But why is there more than that? Any idea?
Maybe it's high temperature.
Okay, could be. It's not, but it's another effect actually. The point here is that it's um, we call that clouds or expansers, right, of dust and gas, and that is mostly hydrogen in this case. So the reason why it's then colored is because they're ionized from nearby stars, right? They're photons hitting the hydrogen. And then, of course, we know there's a color change. That's why we have color on planet Earth as well, for example. And they emit light in consequence. Huh? So when you now have something like this is from the Orion region, and it has okay, it needs a bit of fantasy, but of what type of creature could that remind you? Maybe. this one, or we make it a bit less large, because it's called after a creature. So it's called the Horsehead Nebula, because it's nebula is
Oh,
usually like kind of a cloud, but out in the universe. And the reason why we can see that is not because it, how to say, it's really there as a solid um, constellation or whatsoever, but they remain here for whatever reason in atomic form and block out the light from behind. So actually, this is a typical effect of, it's like a shadow, kind of, because they block the light from whatever is going on. That's why it appears like this. So there's a structure there, but we only see the structure because it doesn't let the light through. So we see basically the Hainsworth, the structure. But of course, it's not like a planet or whatever. It's just another gas constellation, which is for whatever reason not ionized, and Hainsworth remains dark. And we see that because of the light around. So that's important. So obviously, whatever goes on, they react to the environment, and we can see that something must go on. There must be something which is enable them to emit light. So they further decay. That is coming closer to the point of what else is there actually, not just the basic structure which we know so well now. So coming back a bit to the various types of particles. In this diagram, what do we see, Chris? Here, what's happening? What is your explanation?
the alpha particles can uh, they're
Say
bigger.
again.
Alpha particles have larger mass and higher charge, so it
Okay.
can ionize more.
Okay. Can you hear me properly, Chris?
Yeah.
Okay, now it's better because it was a bit distorted for a couple of seconds. If you can just say once more what you said, because it was just kind of electronic garble.
The alpha particle has more mass and more charge, so it has more ionizing power,
Okay.
so it cannot go through much matter.
All right.
And
Good one.
the beta particle is uh, much less mass, and uh, it has half the charge. So its ionizing power is less, and so it can go through more matter.
Okay.
And the gamma ray is not not it isn't uh, a particle, so it it also doesn't have charge, so it can just go through more penetrative power.
Okay. Does gamma ray have a mass?
No.
Right. Exactly. A good one. Yeah. So yeah, that's the gist of it. So with the alpha particle, and you can see that, of course, from the experiment or from the dates of the experiment. At that stage, they took what is comparatively easily available. So we have the helium for the alpha particle, and if I take the helium, then of course, as we then finally figured out, we have 2, 4, right? For this one. So what is now, so um, like we said, if we would include the electron, then of course, then it would be a bit different. So that's usually the difficulty, to say, this is an alpha particle, but of course, from the outside, it looks like any normal helium atom, right? Because it's 2, 4. So what's different, right? But because it's a particle, something must have happened. And the something must have happened is because well, it doesn't have its electrons anymore. So it's just a nucleus without the electron. And we call that it's comparatively slow. So it's about, that's all relative, of course. It makes 10 to the power of 6 meters per second. The beta minus, the beta minus, how do we use is a typical electron, of course, right? So, of course, so that means, in other words, this is what we do. The mass is not exactly 0, but in the context of our usual writing, we label it as 0. The mass relative to the proton, this is something I didn't include here. So this is the mass relative to the proton. Of course, we have 4. Here we have 1 over 18/40. So basically, it's not existing as mass. And of course, here we have the minus. That is becoming, that is already much faster, 10 to the power of 8. That's one of the reasons why it can penetrate further. Right, it has a high velocity, so that helps, of course, to penetrate certain material. And there's no difference between the beta particle plus as well. So, of course, but to be complete, what would be now the difference to the beta plus particle to the beta minus, Chris?
The beta plus has +1 charge instead of minus.
So we have something very strange, right? We have a positively charged electron, which is theoretically was considered as not being possible, right? So the rest is the same. So it's still an electron. Well, at least we call it. Later on, we realize we have to call it different. Of course, it's the same velocity or speed. And gamma ray, of course, is then, surprise, surprise, 0, 0. Huh? So it has no charge and it has no mass. And it goes at the speed of light. 3 times 10 to the power of 8. Huh? So basically, the beta goes at the speed of light, close, but by factor 1 to 3 not. Whereas then the gamma goes by factor, goes at the speed of light, so it's 3 times faster. And the difference with the other one is obviously 100. Okay, so that is part of the explanation. Mass. So of course, one with the big mass has a different dimension. So of course, it will get stuck as well to some degree. Velocity is one thing, but its size has a certain size, so hence it gets stuck. This one is small, it penetrates, it's faster, but then it gets stuck as well at a certain thickness of a certain material. Obviously, structure. Paper has no real structure. That's why they go through. Alpha already gets stuck. Aluminium, of course, metal, grit, so it gets stuck. But gamma is too fast and has no mass, so hence it just goes through. Okay. That was just some illustration. I think we can skip that. What happens here? Same for the gamma. That's a typical way to write it. Of course, important when we come closer to your question, what happens here actually with these two?
The annihilation.
Exactly. So theoretically, that's one of the puzzles we have still. It's like when we had the puzzle of why is an atom heavier than we would expect when we think of only the protons. Same here. Why is there even matter, right? If you always have a plus and a minus, then you would have no existing matter, actually, only radiation maybe. So there would be no universe, right? Because they always annihilate each other. Then you have whatever, gamma or whatever ray, but we would have no other matter anymore because they always compensate each other with the plus and the minus. But in reality, they don't. So that's one of the big puzzles still. And related to that is the issue of the so-called dark matter as well. Huh? That's related to that. So from that one, we know not just plus and minus. That was a huge breakthrough. And remember from the electricity, what was the very original model of the charge of the so-called current at the beginning? Not nowadays, but at the beginning. What was the idea of the charge of that current?
Huh?
Plus,
The,
plus or minus?
minus?
Not at the beginning, right? Remember, when you think of the does the current flow from plus to minus or from minus to or the other way around?
The conventional current is the flow of positive charge from the positive to minus.
Exactly, huh? Exactly. So that because like you just said, it was thought to be a positive charge, so a positive current. There was for whatever reason, right? And we kept that model. That's why we always have to think: do we talk about conventional or electron flow? Because now we know the carrier of the charge is actually the electron and not the not the proton. So that makes a huge difference. But because of that, yes. So that was a huge breakthrough. Huh? At that time, there was only the thinking there's something plus. Later on, it was identified no. There's a whole atomic model, and the carrier of the current or the charge is under normal circumstances the electron. That's why we have electricity, and which is the flow of the electrons. But now we go further. We go into the atomic structure. We realize there must be the neutrons, otherwise we can't explain the mass difference from the theoretical model of adding up the protons. That's already a huge breakthrough. To identify the proton is identifying what type of element we have. And that is corresponding, of course, to the number of electrons, otherwise it would not be neutral. So obviously, beyond the surface, it's not neutral. It's the sum of plus and minus which makes it neutral. That was a huge breakthrough, obviously. That I think for the last 100 years plus, that made all the breakthroughs possible we encounter these days. Huh? Now the next step is waiting and to say, okay, first before we go now into that one, we say, well, what about the intensity, the kinetic energy? That's something we have to keep in mind. That's important. And can you explain to me what is going on here?
Not all the. So there are electrons that uh, have less energy.
Okay. So there exactly that. So, or in other words, that the strange, the beta particles have a wide range of energies, right? And when we think from Newton, we know we have kinetic energy, right? That is obviously related here. So that's
Always have to do this.
difference. What is that equal to as well, Chris?
Hello?
Yeah, do you still hear me?
Just now my internet cut off.
Okay. Do you still hear me?
Yeah, yeah, yeah.
Okay, the picture as well. See?
Yeah, I see it.
Okay, all right. So the point is potential difference, right? In the standard electric circuit, and of course we can utilize that as well on the atomic level in the end. So what does that potential difference stand for? What is it actually?
The energy each coulomb carries.
Yeah, yeah, it's the energy transfer, right? So when we go through a so-called potential difference, which we have volts, right? Then on the other hand, there's an energy transfer. Huh? That's very important to remember, like you do, right? Or we could say as well work. But as we can see that, well, the electron is actually has to do work, like when we know gravitational field, electric field, there's a lot of similarities there. Huh? And the charge is for an electron. Oops, an electron. Do you remember eventually that number, Chris? If not, it's okay. Just ask.
I think 1.6
Okay, good.
times 10 to the power negative 19.
Yeah, very good. Exactly. Yeah? So that's the charge of one electron. And this one we can express a bit differently. So we can say the energy, and we can say, of course, it must have potential difference, and that's the charge. That's a few times V. So in other words, let's go back one here. So we have 1.6 times the power of 19 times 1 volt times 1. And then, of course, surprise, surprise, we get 1.6 and 10 to the power of minus 19. And then, because we get energy, so henceforth, this is then joules, and this is what we call the so-called electron volt. Huh? That is, so the reason why we do that is because, so if we have now one electron, which we know has a charge of 1.6 times 10 to the power of minus 19, and we take 2 volts, what is then the energy? How many electrons volt do we have then? Chris, when we say 1 electron volt is the charge of 1 electron going through a potential difference of 1 volt. Maybe I highlight that. So with the what times 1, that's this one. So times 1. So that's going through the potential difference of 1 volt. And of course, the charge is of course this one. That's the charge of the electron. So we get. So if I now have an electron going through a potential difference of 2 volts, how many electron volts do I get, or what energy do I get out of that? Or
It's
have
just
to,
a double of that.
yeah, genau. So that's very important to remember. That it's really related to, of course, you may say how many electrons you have. Okay, that's one thing, but we are dealing with atomic experiments. So in tendency, we try to just do it with 1 electron. That's because that has a very low mass. It's comparatively easy to accelerate, for example. And that's why we, of course, then use big voltage in order to put in a lot of energy. So which means, of course, if we now have a potential difference which is extremely high, then of course we can whoosh accelerate the electron accordingly, because it's a huge voltage applied to 1 electron, which is a huge energy, which means we can accelerate it accordingly. So there's a bit of a basic link with all these issues, which we are not going further, but important to keep in mind. And you see here, here's a link between this kinetic energy, which we express in mega electron volt. So that means if we have 1 electron, then how many volts did we apply? Let's say here, with 1 mega electron volt of energy. How many volts did we have to apply?
What?
So in other words, mega electron volts. And we apply to 1 electron, so we still have 1.6 times 10 to the power of minus 19. But how many volts do we have to apply in order to get, well, for example, 1 mega electron volt?
Or milli.
Exactly. So we get 1 megajoule. Exactly. Same thing. So 1 million, 10 to the power of 6. So there's a very simple link actually at the end of the day. So that means we had to apply 1,000,000 volt. That's really a lot, in order for that 1 electron, and then we get that mega. And you see here, that's the kinetic energy we get, because of course that electron gets accelerated. It has a kinetic energy because it goes from A to B, so to speak, within that potential difference. Okay, so that is something which is not really covered there, but I think it's important to keep that in mind of what we are talking about, right? What is that electron? And the reason why we go into electron volts is because otherwise, if we would just express it as joules, you can see it here, right? They are so tiny, the energy levels, then you would always have to say 1.6 times 10 to the power of minus 19. And like we said, if you applied 2 volts, then you would have 3.2 times 10 to the power of minus 19. I mean, scientists are ultimately kind of lazy or very smart. You can look at it from 2 angles. Hence, they say, you know what, instead of saying this, I find out something new and say, oh, hey, I know there's an electron. I have 1 volt applied. Hence, that's my energy level. So in the future, I'm not talking about 1.6 times 10 to the power of minus 19 joules. I just talk about 1 electron volt of energy, because it's energy, because of the simple relationship between charge and voltage, which is work kind of, but it's energy the same. We call it 1 electron volt or 1 mega electron volt. Makes life much easier when you look at it here. You just have to keep in mind what type of charge are we talking about. When we ultimately use the SI unit, that we say, okay, what does that mean in energy levels in joules, for example? Then you have to remember, okay, mega means 10.6, but it was applied to 1 voltage charge, hence we get 1.6 times 10 to the power of 13 in that case, and minus 13, or you can call it as well still 10 to the power of minus 16, minus 19 megajoules then, you know? So we can play with that. I still call it megajoules and leave it at the minus 19, you know? Okay. For the equations of radioactive decay, did you go through that, Chris? Did we cover that, or is it okay to skip it?
Which one?
The equations of radioactive decay.
Yeah, I already did it.
Okay, all right, we leave that, huh? Okay. So now the point is this one, that's now coming to this one. So what do you see here? I mean, of course, there's a lot of information, but you can focus on one specific. And the point here is to say, okay, probably there's more than just the neutrons and the electrons and the protons, because we already know we have billions of molecules, and it was fantastic to say, well, but actually, you know what? These molecules are made of atoms. Okay, big breakthrough, roughly about 92 atoms, which really count. The rest has really short half times, so they decay instantly. You can hardly ever see them. So about 92 atoms. With that, with a set of 92 Lego blocks, different ones, you can build the whole universe. That's actually, wow, quite impressive. And furthermore, with 3 types, 3 particles, we can build all these atoms. You know? So the suspicion at some point came then from further experiments, well, there's probably something more. So we go from billions of molecules, 10 to the power, I mean, x times 10 to the power of 9 molecules. We could go to only 92 atoms. We could go to 3 particles. And then this is, then, well, are these particles the end of it? Are there only the 3 ultimate Lego blocks, so to speak, which made then the other 92 atoms? Or is there something further? Huh? And experiments like this picture show that. Have you seen something like that before, Chris?
Yeah.
So when you look at this one, what happens here?
It's the collision.
Okay,
And
and what?
I think it's the collision of either a proton or a neutron.
Yeah, okay, could be, huh? For example, it depends. All right, and but then what what does that indicate here? Because if you have a fundamental particle like, well, let's say a neutron or whatever, one of the two, what depends on what we deal with. If that collides and it would not consist of something else, what would happen? A bit like what we had at the very beginning with the alpha particle.
Then it will just deflect.
Exactly. Yeah, very good. Exactly. We just come back. Just say, okay, boing. It hits the wall. It hits another one. It comes back. Classic Newton. But it doesn't. Or they would have an impulse, whatever. No? So, so that it splits. But how can something which is the core of everything, this one, split? Theoretically, cannot. Obviously, the model is wrong. Huh? So we have to have something which explains that in more detail. That's where we go into the families of particles. Huh? And that's where we now come into that part, which you said. Um, so which one in particular, Chris, did you say you're not so clear or would you like to go? Was it the leptons or the hadrons or which ones was it? Oh,
The hadrons.
the hadrons, huh? Okay. Okay. And let me just see. Because the leptons are so quarks. You're okay with the quarks?
Yeah.
Okay, huh? They always show up in questions, guaranteed, right? So that's something. It's not that difficult, but you have to be sure about what it is. Huh? Then you can handle the quarks. Do you know just nevertheless? Do you know the subtypes? Oh, in other words, does one quark usually show on its own as a standalone one quark?
Huh?
Does a quark, one single quark, typically exist on its own?
Uh, they're in pairs and they also have the antiquark.
Yeah, exactly. Very important. So quarks are. That's why it was difficult to identify at the beginning because contrary to a proton, they don't really exist on their own exactly. Huh? So as we just said, they come in groups, huh? And then they have their own logic behind. Okay, so just to come back quickly to that, that's good. Halons. Okay. Have you covered the hadrons in more detail, even, Chris?
Huh? Uh, no, just I just know
Because
that
you know that. Sorry, yeah, please.
there's the neutron and proton, and there's also like the mesons.
Yep. Um, because they are part of the quarks, huh? So that's why the baryons and the mesons are part of the quark arrangement, if you want to say so. Huh? So, in other words, I mean, just quickly, huh? Because the hadrons we usually don't cover in detail because it's really it's quite comparative. The leptons, there's a number to it. We can deal with that. The hadrons are actually a bit more complicated. Um, they are composed of quarks, and they include baryons or mesons, of course. So the complication here is that the hadrons are made of structures of quarks, huh? And that's why we need to cover the quarks quickly. So, do you know what the charge of the quarks are? The two main groups
Quark and
compared to an electron.
huh?
Compared to an electron. Just the basic quark, huh?
Like up down.
With the letters.
up and down, and the strange and charm, and the
Yeah, exactly. So we have the
top
inclusion
and
of
bottom.
these charms. Huh? Yeah, okay. Yeah, yeah. So it has the charge of plus or minus 2/3 of an electron charge. And that's why we have then here the UCT. And on the other hand, we have the DSP, yeah? DSP structure.
But for the negative one, is it not -1/3?
Ah, what did I say? 2/3. Yeah, yeah, sorry. Thank you. So the charge difference, so minus 1/3. Yeah? And the antiquarks, what are the antiquarks then?
The anti up down charm strange and top bottom.
Okay, so how do we denote them typically?
Like with a bar on the top.
Yeah, okay, all right, okay, okay. So that's how we then start to combine them, no? And there's a lot of them. So then you have the, in order as they are coming in groups, then you have the baryons, and of course the antibaryons. So quark, 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 right? So to simplify that, we call them, we make them Q, 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 because they consist of three quarks, or antibaryons, of course, consist of antiquarks, huh? Antibaryons, huh? And now here we go. Um, the funny thing is then, of course, now, would you remember how's the proton, right? Because the proton is obviously one we see. So if our concept is true, that the three particles we knew so far, proton, electron, neutron, and we say there's a substructure, then, well, now it's a question, is it the quarks or whatever? Doesn't matter. In this context, we know it's the quarks. So obviously the proton must be made of, in this case, quarks. Could have been different, but now here we know in the meantime it is. So we have the proton. Do you know the quark content? So which three quarks form a proton?
It is up, up and down.
Yeah, there you go. Up. Sorry. Let's take it in three. Huh? Up, up, down. And what is the charge Hainsworth?
It's +2/3 +2/3 -1/3.
Okay, and the resulting charge?
Just one.
Plus, exactly. Yeah? So that's the funny thing, right? Because it's again made of subparticles, the proton. What we convenient. That's why, of course, is it really 2/3? Is it really minus 1/3? It's of course a model at the end of the day, but which is actually quite, it works, because in the end that explains why we have a plus charge of one. But maybe somebody else could have come up with a different concept and it would still explain everything, as long as the parts fit of the whole model. So we found one way, or those persons who did it, so that we can, what we identified before, when we said a proton has one plus charge, an electron has one minus charge, and now we can explain it with the structure. But of course, one leads to the other, right? By having said the proton is +1, maybe in a different universe, somebody would have said it's plus 0.5 for whatever reason. Like somebody would have said the day has 20 hours instead of 24. Huh? Same thing. It's always a model issue, not to forget. Of course, we have the antiproton. What would be the charge of the antiproton, Chris?
Uh, -1.
-1, huh? And of course, what would be the structure of the negative quark content, as we call it? What would be the quark content of the antiproton?
Anti-up, anti-up, and anti-down.
Yeah, exactly. Huh? That's why it's actually quite a good model. Huh? Or every good model in the end is comparatively simple. What would be the neutron? What is it made of?
Up, down, down.
Yeah, good. Yeah. Up, down, down, and henceforth, what is the charge?
0.
0, huh? Exactly. Yeah. So, well, perfect. Nice model. So that's the baryons. So if we now go into the mesons, do you remember how many quarks there are for the meson
Uh,
and how they are made of?
one quark and one anti-quark.
Yeah, no, that's very funny actually. Huh? Kind of. You think a quark and an anti-quark, well, there would be nothing. I mean, at least from the outside setup, like a plus and minus, it results in zero, but they don't. Huh? So now, if we and they're quite some that we usually don't deal with them, but just to say, one which is usually quite famous, or at least always mentioned, that's this one. Huh? Do you remember how that's called?
Uh, just is it just called pi plus
Yeah,
misons?
could be. It's cool. Yeah, it's a bit fun. It's pion because of ion, kind of. So when I give you the K minus, what would that be? Just follow the K.
K ion.
Okay, exactly. And then, of course, being lazy, they omit the I, huh? So K on. Okay, when you look
Okay.
at the structure, what would be the structure of the pion? Do you, or let's jump ahead first. What would be the charge? Why do we say it's a plus, the pi plus, right? What would be the electric charge most likely?
Plus one.
Plus one, huh? Because we deal with plus one and zero, at least on most cases. And hence, well, what is the K on there for? Or the K minus?
Minus one.
Minus one, huh? Now, in order to come up with that charge, and we know it has to be a quark and an anti-quark, so of course there are certain combinations possible, but which one is it?
Uh,
Because it's, of course, you have more than one solution in tendency, right? So that one is, I mean, you don't have to remember that, of course. It's just, I just want to ask you, but otherwise, of course, I give you the answer.
maybe like up and then anti down.
Yeah, good one. Yeah, exactly. Huh? So very nice. Huh? So that we go across like this, and henceforth, uh, with the, okay, just for the sake of it, and do it here as well. Huh? Okay. What about the kaon? What would that be?
Maybe anti up and down.
Yeah, could be. It's not. That's fine, right? Because there's more than one. So it has to. You have to identify. I mean, you, the scientists, not me. The scientists have to identify that, and it's an SU anti, huh? Okay, and so on. So there's a whole family of baryons and mesons. So of course, the reason is okay. So obviously, we need to know more about the quarks, and as they are not coming individually, they come in groups. For us, more interesting enough the triers and the two groups of three for each of two. They have the specific name, baryons and mesons. Baryons are obviously anti as well, either everything normal or everything negative. Mesons can only be Q and Q anti. And then we have many combinations in order to get the respective charges. Huh? So maybe just to complete this one here, because we have a zero as well, then we follow the logic above. Then we have the B0. That is strangely no other name. It's just B0. That, of course, is zero, obviously. And this one is a D beam, also D anti beam. Huh? So from the outset, funny enough, we have plus, minus, and zero, and here plus, minus, and zero, but completely differently made up. Huh? This was a huge breakthrough, of course, to realize what we usually call protons and neutron, antiproton. Well, we usually think of electrons, which, of course, the antiproton and the electron are not exactly the same. So that's what we thought is the world, but it's not. Huh? So we can have multiples of these charges coming from very different structures, which makes actually kind of sense ultimately, right? Goes a bit back to here. That's why we have what we call nowadays the standard model. Huh? That's the standard model, which still does not explain everything, but it explains a lot already. Huh? So that's the third level nowadays. How we go ahead, and now the hadrons, they are composed of quarks, of baryons and mesons. Huh? And there's a strong interactions between all hadrons, and that is the huge difference between hadrons and leptons. Huh? So in other words, so if we what when we talk about leptons, let's make it like that. Huh? Leptons. Actually, I make the shortcut. They're electrons. They belong to the leptons and neutrinos, not neutrons, neutrinos. And they are unaffected by the stronger nuclear force. That's the funny thing, and that's why we have that major difference between the hadrons and the leptons. These are the protons, they're part of it, and the neutrons. It's just that we can give them into the group, but the key issue here is strong nuclear force. Not affected. Be affected. Affected. Yeah, sorry. Affected by the strong nuclear force. Huh? So that's why. So this is the major issue in order to make the difference. And hadron is more bulky because, well, we talk about protons and neutrons, so they're crystal clear, more bulky than electrons and neutrons. Huh? And you can imagine from the first mass or particle accelerators, it's a massive difference if you have to accelerate an electron or a proton. Huh? We know that. We talk about factor 10 to the power of 4. So you need to apply much more energy in order to accelerate it. Huh? So that's why in the beginning all the experiments are always made with electrons. So when you go into electron volt, the charge is the same. We know one proton has the same charge as an electron, but it has a different mass. So that comes into play then, and hence so we have nowadays a large hadron collider in Geneva, and that was the one which was being used in order to find this family of this family to identify further. And the reason why this was made is the Higgs boson. Huh? So that's the one which is, because there we go into so-called bosons, like the Higgs boson, for example. And let me just see. Okay, so let me just, because there's one, the standard model, which you obviously, you don't have to go into the details, but if I try to make it here, we have the UCT and we have the DSP. Huh? DSP. So we have the quarks. Huh? Let's make them. No, I could have made them color-wise already different. So UCT, DSP, DSP. each one of them. No? And I'm not listing it here because that goes really into the detail, but of course it's about the mass, the charge, and the spin. No? So typically, for example, we would have the mass of the up quark, we would have the charge of the up quark, and we would have the spin. And when we go into these differences, then you can see, of course, first of all, here we differentiate by the main difference between top and bottom, also in this one, is squaring out the charge. Huh? Otherwise, it's the same. Of course, we can go into the anti, but we don't, because that's not the standard model. Then just you can go into the anti as well. So quarks is one thing. Now, when we look at the leptons, because the interesting thing is that they are listed here. We can take the electrons here. Actually, we have the electron, we have the muon, also from the mu, we have the tau here. And they differentiate very much in mass. They still have the same spin, for example, like the quarks, but they have a different mass. And then we get an electron neutrino. We got a muon. Oops, that's one too many. Excuse me. The muon neutrino. And we have the tau neutrino. So they're all part of the electrons. Again, different masses, and of course, they have no charge. That's the point here with those. So those here are minus charge, these three, and they all have no charge. So we start to see a bit of the logic of the arrangement. Now we have the bosons. They're coming completely out of in a different way. The reason I have to show that to you, don't have to remember that, is a bit to explain why the hadrons are then so important, why we go into that standard model, because we have the photon, and of course the photon has no mass. We have the gluon, of course, has no mass either. We go into the Z boson, this one here, and we go into W boson. That's here. The first three all have zero mass. Of course, photons has no mass, right? But the W boson can either be plus or minus one, so that's very strange. But from a theoretical model, explainable. And now the one which is missing is the so-called Higgs boson. That's this one here. And when you look at the logic of it, it must be 0, 0. That's the point. No? So it has no mass, no charge. It has still a mass, excuse me. I said no charge. Huh? So the photon has 0, 0, 0, 1. So I have to be very precise here. Has no mass, has no charge, but it has a spin of 1. So when we go through the logic of the whole build-up, then we can realize that the Higgs boson actually has a mass. I just call it A now. The effective value doesn't matter. But it has no charge and no spin. So it's like a logical model, like from the atomic structure, where you say, well, that should exist. So you would have something, a particle, which has mass, but it has no charge and it has no spin. That was identified in the 60s, actually, theoretically, was when the model started to evolve, the Higgs boson. But it could only be shown later on in the experiments back ultimately in 2012. And that's where you needed the Hadron Collider. When you have protons, neutrons, so you smash protons into each other in order to, well, actually destroy them and then identify the particles which fly out of it. And because, on the other hand, we know that the hadrons are made of protons and neutrons, they are affected by the strong nuclear force, so they are really stable. They have the interactive forces to keep them together, so you need really massive kinetic energy smashing those particles. Particles is now a bit difficult to say because we used to call protons particles as well, but then you want to have the subparticles, which we now know is, for example, made of quarks. And then you could identify the missing one. So it was really a matter of getting the necessary collider in place with all the necessary forces in order to identify such a particle so that you could smash something massive with such force that ultimately that particle, basically like what we have here, also this is not the case, comes out of that collision, which then would prove that, because I smashed that and I can measure this, that's why this is existing truly, not as a theoretical concept only. So, and as we say, it has mass, but it has no charge. So obviously it cannot have, well, a charge, so you can't measure any charge, no potential difference because it doesn't carry a charge. It has no spin, however you measure the spin, but it has a mass. So it's different to a photon, for example, when you have an experiment which emits something which has no mass, no charge, but it has a spin, whereas the Higgs boson has no spin, no charge, but it has mass. And that's why these hadrons are so important ultimately to complete the family. And the substructure of the hadrons is really complicated. So that is something which is not covered in detail because of the resulting forces between the various involved particles of how you build up such a hadron. And they are combined, and as we know, protons, neutrons, they are both built up of baryons, which mesons. And that is in the end what we have in the hadron. So the protons and neutrons are just one of many possible ones existing. And the reason they exist is because you have all the combinations of these various quarks, which we identified before here, from the mesons and the baryons, and how you combine them. And because they have strong forces in between, well, that will be the interesting part which happens. So to close that, and then for today, you have something like, imagine you have a pattern, so they are arranged in a certain pattern. Let's make it like this. And you go like that. And at these points here, and then you say, okay, here I have the plus level, +1 level. I have the 0 level, I have the -1 level of strangeness. And then you can say, well, in this one, and here is the charge. So that this is the strangeness on this one, the blue one. And here you do the charge. -1, 0, +1. So this is the charge. So obviously you have the points in between, so to speak, where you can identify that. Let's make them orange. So here you have a K0, and here you have a K plus, and here you have a pion minus, you have a tau, you have a pi plus, you have a K minus, as here in this interactive point. You have a K plus here, and you have a K0 here. And then you have interactions. You can even have here, actually, this is the strange thing, you can have actually here as well a pi 0. And then you can have an interaction between these two, for example. So they always go in the diagonal, that's why this came up like this. Here. And here. Huh? So there's a link between these two. Same strangeness, and that's why, based upon the, for example, the eta here, that was predicted because of that logic. That it must be existing like that. Huh? So that's why you see the hadrons are really strange creatures. So for us, the bottom line is to know the hadrons are ultimately, or the other way around, protons or neutrons are in the group of the hadrons, and they are affected by the strong nuclear force. And because of this combination, this is part of how the hadrons are organized from the various mesons and byrons. So the quarks are the lowest one, then they're organized in byrons and mesons, and then you organize them again in a certain way, which is resulting then in the hadrons. And then you have this strong affection by the strong nuclear force, which in consequence, in that case, said, well, there must be a certain combination which can lead to that Higgs boson. Like at that time, it was like that the eta must be existing. Huh? Is that helping, Chris?
Yeah.
So the bottom line is that leptons, they are low in mass, hadrons are massive, protons and neutrons belong to that group, and they are the arrangement of our baryons and mesons is resulting in the hadrons. Huh? Which one of it is a proton, for example, or another one is a neutron, but there are many more. More than that, we don't have to explain. If you know already that, there's more than you need to know, so to speak. Huh? So it's good that you have the question, but on the way to on the level to explain, this is just get the structure into place, which you have, which is good. What belongs to what? Then the hadrons are combinations actually of baryons and mesons. So, which proves they are part of a further complex structure. Huh? So they're not just a proton or a neutron. Okay, we have the proton here on its own. Yes, we have that. But when we talk about the hadrons, that's combinations. They just belong to that group of the hadrons. Huh? Okay, all right. For next time, Chris, what would you like to do?
Practice
on these.
On this topic first, and then can we do like practice on the general for AS?
Okay, so just a general test.
Yeah.
Yeah. Okay. Yeah. So basically, like a cover it all test, huh? Or past papers, huh?
Yeah.
Okay. All right. Okay. Okay. And then you review the atomic structure. Okay. Fine. I've jotted that down. Okay. Good. Then see you next Friday, huh? Have a good week. Thank you.
See you. Thank you.
Bye.
自在就係唔受框架所限。Acuvue Oasis
Constantino, que vale pound for pound.
Little giant.
Flexionadito. 10. Más flexionadita la pierna. ¿Ah? 1, eso. 2, 3. Eso. Vamos. 4. Explosivo. 5. 6. 7. 8. 9. Una más. 10. Abdomen. 20 segundos. Venga, señorito. Cruzado, cruzado. Van 10. 15, 5 más. Tiempo, Saúl. Sacando el pecho y la mano agarrándolo fino, Saque el pecho. Eso. Venga, Saúl, bien, 30 segundos. Ahí respiras, ¿ok? 30 segundos de plancha.
Te va bien, José. Nos vemos mañana.
Muy bien. 5 segundos.
¿Perdón?
Que lo flexiones un poquito. Así. 4, ¿sí? Sigo, 5, 7, 8, 9, 10. 20 segundos.
Nos vemos mañana.
Venga, nos vemos. Cruzado, venga. Rápido, 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 rápido. Eso es Saúl. Van 10, Saúl. Venga, 15, 5 más, venga, vamos. Vamos, vamos, cruzado. Tiempo. Ganando, Saúl. Bien, saca el pecho. Eso, Saúl, ya.
Me llamaron más de una ocasión.
Pasado, presente.
Arriba, arriba, arriba.
Un poquito más abajo de la foto. Mete la cabeza. Eso, Saúl. 5 segundos más. Tiempo, señorito. Bien hecho, ¿eh?
Who that? Oh shit.